Hello, and welcome to the lecture on mixed integer nonlinear programming, which is part of the summer school Command-Role Optimization at Work. Let's start with an introduction. First, I will give an overview of this lecture and of what you should be expecting to learn from it. After that, I will go on to the subject of this video, and I will introduce mixed integer nonlinear programming and the types of problems that it solves. Then I will briefly discuss what solving a mixed integer optimization problem means, and what main tasks are involved in the solution process. Having introduced this structure, I will talk about what the presence of nonlinearity means in this context, and what difficulties it adds to each part of the solution process. This is clearly a large and complicated topic. Therefore, this lecture is going to be something of an excursion into the world of MINLP. After this excursion, you should have a general understanding of some of the key notions and definitions that are used in mixed integer nonlinear programming, and you should have an overview of what methods there exist for solving these problems. Then you should also have a general understanding of some of those methods, and a more detailed knowledge of some chosen components of these algorithms. And finally, I'm going to share some practical tips, that is, some things that I find useful for people either working with formulations of mixed integer nonlinear problems, or in solver development, or perhaps both. Because this lecture is a part of a larger course, it is assumed that the viewers have already listened to some of the previous lectures and are familiar with the material presented there. First of all, the viewers are expected to be familiar with some notions of optimization, such as what an optimization problem is, what is its feasible set and how it can be defined, what an objective function is, what are solutions, and so on. More specifically, the viewers are expected to have some knowledge of mixed integer linear programming, such as what a mixed integer linear program is, what is an integer variable and why it adds difficulty to optimization problems, and what is a continuous relaxation, and so on. And finally, some knowledge of algorithms is also assumed, and in particular of the branching bound algorithm for mixed integer linear programming. The viewers are expected to know what the branching and bounding are referring to, then what a primal and dual bound is, what an optimality gap is and how it is used, what is pruning of a node, what are cutting planes and how are they generated and applied, and so on. And also I should mention that I am going to repeat some of these definitions, but it is certainly going to be easier to follow the lecture if you are already familiar with them. This is a general form of a mixed integer nonlinear program. Some parts of it you will find familiar from the mixed integer linear programming lectures, such as the linear objective function. The assumption that it is linear is without loss of generality, because one can always reformulate a program with a nonlinear objective function as a program with a linear objective function. Then we have variables with bounds, and some integer variables. And now we come to the part that is specific to mixed integer nonlinear programming. That is the constraints, some of which might be nonlinear. We have few assumptions on the functions g that define these constraints, namely that g must be continuously differentiable, and that it must map the domain of the x to some rational numbers. We distinguish two important cases. The first case is when all of the g's are convex. In this case, we have a convex MINLP, which means that when the integrality requirements on a subset of x are dropped, we obtain a convex nonlinear program. And the other, more difficult case is when some of the j's are nonconvex. Then we have a nonconvex MINLP. One might ask, where does the need to include nonlinear functions into the formulations of optimization problems come from. So let me show you some connection to the real world. One very common example of a nonlinearity comes from the need to find a variable fraction of a variable quantity. This implies multiplication of two variable terms, and this is nonlinear. A practical example of such multiplication occurs, for example, in water treatment units. Here, the quantity is the level of a contaminant in the water, and the fraction is defined by the removal rate of the treatment unit. But the removal rate itself depends on the configuration of the treatment unit and therefore is variable. And hence we have a multiplication of two variable terms. Then sometimes nonlinearities occur naturally because of some physical laws. This is the case, for example, in alternating current optimal power flow, which is the problem of optimizing over an electrical network. And a somewhat more immediately obvious example is distance constraints, where we have quadratic terms. And of course, there are many more interesting and useful applications where one has to use nonlinear functions in order to model them. Solving an optimization problem means finding a solution that is both feasible and optimal. However, in the case of any mixed integer programming, these two goals usually cannot be achieved immediately simultaneously. Therefore, MILPs are usually approached from two sides. The primal side is all about feasibility. Here we want to find feasible solutions and hopefully to find solutions that are good. But we have to accept that usually we cannot achieve or prove optimality. However, this side is very important for practical applications, because constraints usually represent conditions that must be satisfied by a solution. And a solution that violates some of those conditions can be useless or possibly even dangerous. However, in optimization, the final goal is to find not just some rather good solution, but to find a solution that is feasible and optimal. And therefore we need the second side, the dual side, which is all about optimality. So here we do exactly the opposite. We focus on proving optimality, but we sacrifice feasibility for the time being. And finally, there is the strategy, which puts together these two different but connected sides and ensures convergence between the primal and the dual sides. In practice, this is usually achieved by dividing the problem using different methods such as branching, decompositions, and so on. And these methods must put together all of the components and provide an algorithm which solves the optimization problem and provides a solution that is both feasible and optimal. Now, what happens when the problem also becomes nonlinear? First of all, there are some general difficulties that are associated with nonlinear problems, such as, for example, numerical issues becoming worse, or nonlinear programming solvers being less efficient and less reliable than linear programming solvers. And these general issues will be encountered on all the sides of the solution process. And then if we look into the algorithms and into the details, then first of all, when you find feasible solutions, then of course now they also must satisfy nonlinear constraints. And that again means solving MINLPs. In addition to that, if the problem is also non-convex, this means that even if we relax the integrality requirements and solve the MINLP, we will most likely not get the global optimum, but only some local optimum. And that means that we again are losing some of the solution quality. Now, how does nonlinearity affect proving optimality? First of all, algorithms have to make decisions between using NLP and LP relaxations. NLP relaxations might provide better bounds, for example, but they are less efficient than LP relaxations. And so the algorithms have to be smart about which to use and when to use them. Then if the problem is also non-convex, then there is another serious issue that if you relax integrality requirements and solve the problem, solve the relaxation, then you will not get a valid lower bound. Because again, you might be you might have just a local optimum, and the local optimum has a higher objective value than the real global optimum, and so that is not a valid lower bound. And to summarize everything about this part, if you look at the big picture, then in the end it is the convenient, in some sense, which I will talk about later, descriptions of the feasible set. And a lot of research is dedicated to finding such descriptions. And finally, we need to bring this all together, which is what the strategy is for. And because the strategy is dealing with connecting all the components, it also has to account for the changes in different components. And one important point which I want to emphasize is the warm starting issue. Warm starting is important in mixed integer programming because when you are solving MIPS, you usually have to solve a lot of relaxations or a lot of subproblems, but in any case, these are going to be in the linear case LPs, but here they might also be NLPs. And the problem with NLPs is that warm starting is not nearly as efficient as for LPs. And that really makes a big difference. And that is the reason why you will see some algorithms really gravitating towards using more LPs and solving NLPs only when this is really justified and really expected to pay off. I suggest that now you take a moment, maybe even pause the video, to recall and make sure that you understand everything that you have heard so far in this lecture. Here I have highlighted some of the things that I find the most important. First of all, I have defined an MINLP problem and have described what kinds of constraints, variables, objective functions they have. Then I have discussed the high-level view of what solving an MINLP or any mixed integer problem involves. And I have described two important parts of the solution process and the connection between them. And finally, I have also described the unique difficulties that nonlinearity brings to mixed integer programming. Let us have a look in more detail at each of the big tasks that are necessary for solving an MINLP. And the first one is finding feasible solutions. For this, we have algorithms that are referred to as primal heuristics. You have probably already heard about such algorithms in the MILP lectures, but I will repeat some of the most important definitions. First of all, the goal of primal heuristics is to find solutions that are first feasible, that is, satisfying all constraints in the problem, and second, we prefer solutions that are of good quality. That is, although we cannot guarantee optimality, but we can still hope and try to find solutions which have lower objective function values. And the best of the solutions that has been found so far by an algorithm is called the best feasible solution or the incumbent solution. And this solution provides an upper bound on the optimal value. That is, we already know that we have at least one solution that has this value of the objective function. And therefore, we are not interested anymore in solutions that have higher values of the objective function, that have lower quality. And if you look at different primal heuristics, then you might notice a common thing. They find some way to restrict a problem so that to obtain a subproblem, for which it is actually possible to find feasible and good solutions. Now, how the restriction is done, we will have a look very soon. And now if you have also non-convexity in your problem, then there is the issue with having local optima instead of global optima. On the one hand, it is alright, because local optima are still feasible solutions. So they can still provide an upper bound, they are still feasible, and so we can still get some useful information from them. But on the other hand, of course, if you have a local optimum instead of a global one, it means that you do lose some of the solution quality. And to somehow mitigate this, there are heuristics that use, for example, multi-start, hoping to find several solutions and choose the best of them. But again, still they are heuristics, and there is no guarantee that we have found the global optimum of the NLP. Here are some examples of primal heuristics for MINLPs, which differ mostly in the way of how the feasible set is restricted. First of all, you can let the LP relaxations do the work. And that happens, for example, in LP-based branching bound, where many LP relaxations are solved in different nodes, and so it is likely that one of those LP relaxations will produce an integer feasible solution. And then the algorithm will call an NLP solver, and we can hope that this solver will figure out the rest of the constraints. There are no guarantees, but this is a heuristic, but there is hope that a feasible solution will be found in this way. Then it is also possible to take into account the problem structure. And one way of doing this is implemented in the undercover heuristic, which fixes not all integer variables, but only some of them, in such a way that the problem becomes linear, and then it solves it as a MIP, mixed integer linear program. And finally, if you already have a feasible solution, which is promising, that is, you believe that it might be close to the actual global optimum, then you might try to improve upon it. And one way of doing this is to restrict the feasible set to the area that is in some sense close to this existing solution, which can be done, for example, by fixing variables, again like in the previous heuristics, or by adding some additional constraints, which will ensure that the new solution will not stray too far from the existing one. The second major task is proving optimality, and in practice this is often where the most effort is spent in an algorithm, which is somewhat reflected by the size of this section, which you can see in the contents bar on top. A very important notion here is that of a relaxation. Although you might already be familiar with it, I'm going to remind you what a relaxation is and how it can be used for finding a lower bound on the problem. Then I'm going to focus on the convex case first, and I will describe how relaxations can be built in this case, both continuous relaxations and linear relaxations. That is where the notion of cutting planes or cuts come in. And once we know how a single cut can be constructed in the convex case, I'm going to explain how algorithms can manage cuts. That is, when and which cuts to use. Then I'm going to continue on to the non-convex case. I will explain which methods from the convex case no longer work when there are non-convexities, what can be adapted, and I will talk about some approaches that are unique to non-convex MINLPs. And another important topic is how to strengthen relaxations. And I'm going to show a couple of approaches for that. As a reminder, a relaxation of a given set is another set which must contain the original set. And if you think about it, the key task here is to describe the feasible set in a not necessarily equivalent, but a convenient way. And convenient here is rather well defined. There is an important requirement that the relaxed problem should be efficiently solvable to global optimality, that is, solvable in polynomial time. And there are different classes of problems for which this holds. For example, convex problems. For this you can call an NLP solver, and if it finds a solution, then this is the global optimum solution. And if it says that the problem is infeasible, then it is likely to be true, although one has to be careful about numerical issues. Or one can also choose an even nicer class of problems, that is, linear problems. There, solving is more efficient, as I have already mentioned, and the warm starting is more efficient too, which is important for algorithms that have to solve many relaxations repeatedly. And there are some things that have to be avoided, such as, for example, extremely large formulations containing too many variables and constraints, or bad numerics, such as, for example, something becoming non-differentiable, or some calculations becoming too unreliable because of the inconvenient formula involved. And finally, some notation. We will denote the feasible set by F and the relaxation by R, and again, the relaxation being a relaxation means that it must contain the feasible set. In the convex case, simply dropping the integrality requirements and solving the resulting NLP is enough for obtaining a valid lower bound. However, it can also be useful to get rid of nonlinearities by building a linear outer approximation of the feasible set. And if you combine the two, then you obtain a linear programming relaxation. In order to construct a linear relaxation, one usually needs to add a number of linear inequalities, which must be valid. That is, they must not cut off any parts of the feasible set. This can be described by this implication. That is, if a point is feasible, it must also be feasible with respect to the linear inequality. And such inequalities are referred to as cutting planes or cuts. In the convex case, a standard way of building a cut is to use the gradient cut formula, or the Cayley cut. Given a convex and differentiable function g, which must be less or equal than 0, and a reference point, these cuts are given by this formula. They can also be strengthened by moving the reference point to the boundary of the feasible set, which is done here in this example. Given a nonlinear and convex constraint, the number of possible valid cuts is infinite. So then the question is, which cuts do we want to actually add to our formulation? Now, as I explain this part, I'm going to show how it works on this small example, where we need to minimize the y variable over the set that is shown here in blue. The first type of cuts are initial cuts. These are the inequalities that initialize the LP before the first LP is solved. And because we have no solution yet, we can only use the feasible set. So you look at what functions we have, what bounds we have, and then one can choose the reference points based on that and build the cuts. And here in the example, we have 3 initial cuts. And then these cuts give you an NLP relaxation, which you can solve in order to obtain the first LP solution. Here this solution is shown by this blue point. But this solution violates the actual nonlinear constraints. So what can we do next? Next we want to separate these points from the feasible set, so that next time when we use the LP relaxation, we get a better solution. And this is done by the separation step. Now we have a reference point that comes from the previous LP relaxation and is its solution. And at this reference point, you add valid inequalities. And therefore, these inequalities will separate x from f. And then you get a better relaxation and you get another solution, here denoted by this blue point. And then you can keep improving until you are satisfied or until you can no longer improve. Like this. And finally, a step which I'm going to only mention but not describe is the cut selection. Even when you apply all these ideas, like the initial cuts and then the separation, then still you might get too many cuts. Not all of them are going to be very useful for improving the quality of the LP relaxation. And this is where cut selection comes in. It uses some heuristic practical criteria for telling which cuts look promising, and then only the ones that look good enough are going to be added to the LP formulation. When dealing with non-convex problems, we are losing some of the nice properties of convex problems. Such as, for example, for convex MINLPs, every local optimum is also a global optimum. However, this is not the case for non-convex MINLPs, although there are some special classes of convex-like problems where this property still holds, but in general you cannot expect it to hold. And another difficulty is that gradient cuts are no longer guaranteed to be valid. And a solution to these issues is to construct a convex relaxation. The best, by which I mean the tightest convex relaxation of a set, is its convex hull, which is defined as the smallest convex set containing the original non-convex set F. However, in general, we have no idea how to explicitly construct the convex hull. And because of this, we go step by step and simplify our task. The first simplification is this. What if we don't look at the convex hull of F as a whole, but we look at individual constraints, GK, and relax the sets that are given by these constraints and then take the intersection? And to do this, most often one would construct a convex underestimator of the function gk, which is a function which is convex and which is less than or equal to gk everywhere in the domain of x. Okay, now this already looks a bit simpler, but in general we still usually do not know how to explicitly construct such a convex underestimator. And therefore we have to look at simple functions. And by simple functions, I mean functions for which we can directly, immediately construct a convex underestimator. And then we look at the function gk, and we consider it as a composition of such simple functions. And then we build the underestimators individually for each of these simple terms and combine them to finally obtain the convex underestimator of gk. And how the combining is done, I'm going to talk about this a little bit later. And here I want to suggest an exercise. Consider two such simple functions, minus x squared and x cubed, and I suggest that you try to write convex underestimators for these functions, given that x is within the bounds minus 1 and 1. Consider a non-convex function g, which is a composition of some simple functions. Combining the convex underestimators of these simple functions in a direct fashion by simply replacing the corresponding terms in the formula for g will not produce a valid underestimator. And to remedy this, there are specialized methods. One is a formula which is referred to as McCormick relaxation, which uses convex and concave envelopes to construct a piecewise formulation which is a valid convex underestimator of G. And another method is the auxiliary variable method. It introduces new variables for each of the simple functions. Now, this reformulation is safe because clearly it is equivalent to the original formulation. However, its advantage is that now we only have simple functions and no more compositions. And these simple functions can now each be handled individually. Once we have the convex relaxation, we can already solve it as an NLP and obtain a valid lower bound. But what if we really prefer to deal with LPs? Well, first I want to reiterate that gradient cuts might no longer be valid. So what do? First, with some luck, it may happen that the convex relaxation is already linear. This is the case, for example, for concave functions, where the convex relaxation is the second. It is at the same time the best possible convex relaxation, and it is also linear. Another example are McCormick envelopes for bilinear products, which also happen to be linear, and we will see them soon. And there are some other functions for which this is the case. However, this is not the case in general. So let us look at the more general case. Here we can first construct a convex relaxation, which would generally be nonlinear, of the nonconvex function, and for this relaxation we can construct gradient cuts, and they are guaranteed to be valid because they are valid for the convex relaxation. Therefore, they will also hold for the nonconvex set that is contained in this relaxation. Let us consider this small example. Here we have a nonconvex set which is shown in blue. For example, we want to try to add a gradient cut, like this. And we can immediately see that it cuts off some points that are feasible, and this is not good. We do not want to have that. Therefore, we do it differently. We construct a convex relaxation, which is shown in light brown, and for this relaxation we can add the gradient cut, which is shown here. The gradient cut is valid for the relaxation because it is convex, and it is also valid for the feasible set because it is valid for the relaxation. And once we have the gradient cut, we can formulate the relaxation as an LP like this, and solve it as an LP. When constructing relaxations, we want them to be as close to the original set as possible, because we want the lower bound that we obtain from them to be as close to the actual global optimum as possible. An important observation here is that a lot of relaxations depend strongly on variable bounds, and tighter bounds imply tighter relaxations. An example of this is the McCormick relaxation of a bilinear product relation, which is given by z equals to x times y. This relaxation is given by 4 linear inequalities, 2 underestimators and 2 overestimators. And if you look at the formula, you can see that these inequalities depend strongly on the bounds. And this is also illustrated by the figures. You can take a moment to compare the two figures and see the difference. And there are some methods for obtaining tighter variable bounds, such as, for example, branching and specialized bound tightening methods, some of which are described in the linked materials. Another way of strengthening relaxations is to use more than one constraint. You might recall that earlier I mentioned that usually we cannot directly build the convex hull of the feasible set as a whole, and therefore we have to simplify the task and consider individual constraints, even if it means losing some of the relaxation strength. And now we are doing exactly the opposite. We are trying to tighten the relaxations by considering not one individual constraint, but by combining it with some other constraints. And usually this means considering some special structures for which this is doable. One example of this is the perspective formulation. Suppose we have a convex constraint g of x less than or equal to 0, but we also have an additional constraint, which requires x to be either within some bounds L and U if the binary variable z is equal to 1, or to go to 0 if z is equal to 0. Of course, we could simply drop the integrality requirement on z and obtain a valid convex MINLP relaxation, and this would be shown by this light gray surface. We would simply require that all the feasible points would be above this surface. However, if we remember that there is an additional constraint, this is not the best convex relaxation possible. The real feasible set that is described by these two constraints is a union of the nonlinear feasible set at z equals 1 and the single point to which the set reduces when z is equal to 0. And to make use of this, one can apply the perspective formulation. This would give us this dark gray surface, which is clearly better than the straightforward formulation because it is tighter. And to obtain perspective cuts, one would construct gradient cuts based on this perspective formulation. Let us take a moment to summarize some of the important parts of this section of the lecture. First, I have introduced the notion of a relaxation and explained what it can be used for and what common types of relaxations there are. Then, for convex MINLPs, I have explained a very important tool, which is the gradient cuts, and I have explained how can they apply it and what the limitations are. Another important notion is that of a convex hull, and I have mentioned why it has a significance for practical purposes of proving optimality. Talking about the practical aspects of how to build convex relaxations on non-convex sets and what the general scheme for doing this is, I have described the auxiliary variable method, which reformulates a function which is composed of some simple functions. And finally, I have described some ways in which the relaxations can be strengthened. Once you know how to find feasible solutions and how to obtain and improve lower bounds, the question is how to put this together in order to solve the optimization problem. And hence this next section of the lecture, the strategy. The goal here is to bring together the primal and dual side and ensure convergence. That is, to find the optimal solution and to prove that it is optimal by closing the gap between the primal and dual bounds. Here I will provide a very brief overview of algorithms that can be used for solving convex MINLPs, and I will have a bit of a closer look at spatial branching bound, which is used for solving non-convex MINLPs to global optimality. This is a very brief overview of algorithms for convex MINLP. Of course, there are many more algorithms than what are listed on this slide, and each algorithm deserves a more in-depth discussion, but there is not enough time for this. So let us start. First, the outer approximation algorithm. It alternates between solving MIP relaxations and NLP subproblems, and it uses the solutions of the NLP subproblems in order to generate cuts which are added to the MIP relaxations. And in the end, there should be enough cuts so that the solution of the MIP relaxation will be also valid with respect to the nonlinear constraints. And this is guaranteed by the equivalence of MINLP to MILP under some conditions, which you can read about in the notes for this lecture. Another method is extended cutting planes. It is rather similar to the outer approximation methods, but it does not solve any NLPs, and instead it simply uses the solutions of MIP relaxations for generating the cuts, which means that the cuts will be generally weaker than those in outer approximation, but they will also be cheaper to generate because there is no NLP solving involved. And finally, another family of methods are branching bound algorithms. They generalize the branching bound methods for MILPs, which you should already be familiar with, but here the difference is that the continuous relaxation is now nonlinear, but convex because the MINLPs are convex. And different algorithms in this family make different choices between solving LP and NLP relaxations. For non-convex MINLPs, it is not enough to only branch on integer variables, because we also need to ensure that we can keep improving the lower bound obtained from convex relaxations until we can close the gap between the primal and the dual bounds. And therefore, we have to branch on variables that participate in violated non-convex constraints, because this will give us tighter variable bounds in each of the resulting subproblems, which can be used to build stronger convex relaxations. And an example of this you can see with this secant for x squared, which improves a lot once you divide the feasible set in two. This type of branching gives rise to the algorithm known as spatial branching bound. Here I have outlined the main steps of the algorithm. You can pause the video if you want to have a look at these steps, and now I would like to demonstrate them on a small example. Here we have some nonlinear set, and we also want the variables to have integer values at the solution. First, we construct a relaxation, and I have chosen to demonstrate it as LP-based spatial branching bound therefore this relaxation is linear. And because it has been constructed before the first branching has been performed, this relaxation is referred to also as the root node relaxation. We solve it. So here the objective function is to minimize y, that is, we want to be as low as possible, and we find the first LP relaxation solution, which is highlighted by this green point. Then we have to branch. We obtain two subproblems for which the relaxations are already better, and the algorithm here has also happened to find a feasible solution denoted by the blue point. Now we can notice that the subproblem on the left has a lower bound that is already higher than the upper bound from the feasible solution. And this means that this subproblem cannot contain the actual global optimum, and so we can prune it. Now we are left with only one subproblem. We have the upper bound from the feasible solution, the lower bound from the LP relaxation solution, and we have some gap between them. And if we are not satisfied with the gap, if it is still too large, we can branch again in order to improve the relaxation. And then we can keep doing that until the gap is below specified tolerance. And the important part here, what enables this algorithm to converge, is that smaller domain implies smaller improved relaxations, and this imply better, stronger bounds. To summarize this section of the lecture, we have had a very brief look at the different approaches for solving convex MINLPs. Then I have told you about another type of branching, which is used for solving non-convex MINLPs in addition to branching on integer variables. And finally, I have explained the main steps of the special branching bound algorithm. SCIP can solve both convex and non-convex MINLPs, and I would like to tell you about some implementation choices that have been made there. First, a few quick facts. SCIP implements LP-based special branching bound. The convex relaxations are constructed with the use of the auxiliary variable method, and the handling of the nonlinear constraints is based on expression graphs. These graphs, also known as expression trees, are a convenient way of representing nonlinear expressions, where the nodes correspond to things like variables or operations, and arcs represent flow of computation. Here I have shown an example of a nonlinear expression and its expression tree. First, you look at the highest level operation. Here it is the sum, and this is going to be the top node. Then you look at which operands it acts upon, and you take the operation which is applied there last. So here it is square, product, and square, and then they go into the next level of the graph. And so on. And also note that the logarithm and the y repeat in the expression twice each. But they do not repeat twice in the expression graph, because the nodes corresponding to them are simply connected to two other nodes each above. SCIP supports a number of different operators, and there are also several constraint handlers for special types of constraints. And the users can also define their own types of operators and constraints. The auxiliary variable method in SCIP is implemented in the reformulation, which happens during the pre-solving stage, and introduces new variables and new constraints in such a way that only elementary terms remain, which can be handled directly. For example, here is a constraint which has this rather ugly function, which cannot be handled immediately explicitly. Therefore, we have to break it down into several other constraints. So, for example, here we see the square root. We can handle that. Then we write g is equal to square root of something and introduce a new variable for this expression under the root. Then we look further. Can we handle a product? Yes, we can. Then it is another constraint, and so on. And so we can reformulate this ugly and terrifying constraint as several constraints, each of which can be handled directly. Now, a few practical tips. First of all, you don't even have to modify the solver in order to improve the performance on a certain model. Sometimes, even formulating the model in a different way can have a large impact on the performance. For example, formulations with tighter continuous relaxations are preferable to those with weaker continuous relaxations. I advise that you take a moment, pause the video to look into this example, and I'm going to continue on to some more practical advice. Experimenting with MINLPs can be an interesting and exciting, so to say, experience. And one reason for this is the performance variability, which also occurs in MILPs, but tends to be even more pronounced in MINLPs. This can make obtaining more reliable results difficult. So how does one deal with this? One way is to use, if possible, large and heterogeneous test sets. This means that, for example, if you're interested in the impact of a certain general purpose feature, then you might want to test on models that come from different applications and have different structures, different types of functions, and so on. If you're interested in a particular application, there can also be some diversity which comes from different instances and different data. Also, performance variability can be used to your advantage. For example, if you permute the model, then very likely for different permutations you will get different results. And this will help you separate random effects from the consistent ones. Then another tip is to use solver statistics. It can be really helpful at understanding what exactly is going on during the solution process and why some things work or do not work. And finally, if you want to understand how some feature impacts the performance, you might want to turn off some components in order to isolate this feature. However, one should be careful when doing that because there might be some meaningful interaction between different components. So if you turn off some component, you might get results that do not really reflect the real picture. However, you might also be able to find some interesting interaction between different components. Now we are approaching the end of this lecture, and I would like to highlight some of the things that have been covered. First, I have given a high-level view of what solving a mixed integer problem involves. That is, finding feasible solutions, then improving relaxations, from which one can obtain better dual bounds, and finally ensuring the convergence between the primal and dual bounds. Then I have talked about algorithms known as Primal heuristics, which find feasible solutions, usually by restricting the problem in some way, for example, by fixing integer variables to some suitable values. A large part of this lecture has been dedicated to proving optimality, and this is all about relaxations. And the tighter relaxations are, the better dual bounds we obtain, the happier we are. And I have covered the cases of convex and non-convex problems. Then I have described the main steps of the spatial branching bound algorithm, and I have talked a bit about how SCIP solves MINLPs and given a few tips which might be useful when working with MINLPs. This concludes my lecture, and I hope to see you at the Q&A session.